Hello chemistry students, this is Dr. Athens creating these videos to prepare you for the Chem 2025 final exam. Thanks so much for all of your effort this semester. It has been my pleasure to work with you. The final exam will be available to you. This is Lee Campus hours, April 25th. That's a Friday, starting at 2 p.m. to 8 p.m., running through Thursday, May 1st until 8 p.m. Please check with your local testing center and verify the hours on their website. When you go to the testing center, you should bring with you your calculator. We don't have a lot of intense calculations. Just make sure it has log functions on it. You need an ID, and you should bring a writing implement. You will be provided with the resources sheet, and you'll be provided with scrap paper. All of the papers stay behind as you exit the testing center. As far as the format of the exam, we're covering chapters 8 through 12, 14, and 18. And you have many multiple choice questions, 64 of them, accounting for 100 of the points. And of those 64 questions, you have 21 that are vocabulary. So it's really wise to review the terms at the end of each of those chapters. Then in Part B, you'll have 5 open response questions. They're weightier questions. They will involve you doing some calculations and then typing in your answer at the finish. Those questions relate to stoichiometry, with and without limiting reactants, percent yield, questions about phases of matter, and polarity questions, looking at compound structure. All right, the extra credit is now past the deadline. As far as what is not on the resources sheet that I think you should memorize, I think you should keep straight the gas laws. So the Boyle's relationship says that when pressure increases, volume decreases, and when pressure decreases, volume increases. This is an indirect relationship. This is Boyle's law. Charles' law says that when you increase the temperature, the volume goes up. So it doesn't really matter what I put as X and what I put as Y. Let's say you control the temperature, so we put that on the independent axis here, T, and you'll see the volume expand like a balloon. This is Charles. This is a direct relationship. Gay-Lussac is similar to Charles in that if I increase the temperature, the pressure inside a closed vessel will increase. That's a direct relationship. And then Avogadro says that if I pump more gas molecules into a balloon, for instance, say you have a bike pump and you're pumping into a balloon, the volume goes up. That's a direct relationship also. So keep straight which gas law is which and which is direct and which is indirect. Okay, Boyle's is the indirect one between pressure and volume. All right, another thing, at the end of chapter 14 you were working with the titration equation. That's not specifically on your resources sheet. It's molarity of acid times the volume of the acid equals the molarity of the base times the volume of the base. Molarity is big M. It's moles per liter. So if I take moles per liter and I multiply by liters, you can see I'm going to get moles out of that. And so basically this equation is saying the moles of acid equal the moles of base at the equivalence point, which is where it reaches neutrality. That's the titration equation. All right, that's it for memorization. Let's now go into sample problems on the various topics, and I have this in chronological order as we work through the chapters. All right, chapter 8's on the mole, and so with that you needed to become fluent in switching between moles and grams, and we introduced the idea of molar mass. So we should be able to go back and forth. So I put a few sample problems here. Calculate the grams of 0.3 moles of hydrobromic acid. Well, first of all, you have to be able to write hydrobromic acid. That's hydrobromic acid. And if we say that bromine has a mass of 80, and this has a mass of 1. We're talking about 81 grams per mole is the molar mass. But we don't have a whole mole, we have 0.3 moles. So if you take 81 times 0.3, you'll get 24 grams of bromine, of HBr. Keeping track of sig figs, that's approximately 20 grams of HBr. Next question. How many atoms of copper are in 10 grams of copper? Alright, if you look at copper, first of all, you should know by now that the symbol for copper is Cu. Copper has a molar mass of 63.5 grams per mole. You're told that you have 10 grams. Okay? So I give you the option. If you have adopted the molar mountain idea, the molar mountain has certain positions on it. We have grams up here, we have molar mass here, and we have moles here. So if you're going to go with this route, we'll say the 10 goes up here, the 63.5 goes here. 10 divided by 63.5 is 0.16 moles. Okay, is that our answer? How many atoms? How many atoms? Alright, we're not done. I need to get the Avogadro's factor in here, right? Those moles times the fact that there are 6.022 times 10 to the 23 atoms in a mole will give me my final answer of 9, I get 3 sig figs here, 9.45 times 10 to the 22 atoms. What is the volume of 1.2 times 10 to the 23 molecules of oxygen gas at STP? Alright, first up, I hope that as soon as you see oxygen gas, you think O2, not O. Molecules, because it's one of the diatomic molecules. Alright, a number like this, I want to move that to be moles. So I take that count and I divide it by 6.02 times 10 to the 23 molecules per mole. And I'm going to get moles out of that. So if I take 1.2 and divide it by 6.022, the 10 to the 23s will cancel, and I'll get 0.199 moles. 0.199 moles. Okay, basically 0.2 moles. That's not our answer though. What is the volume at STP? Okay, I hope that you remember that at STP, which is standard temperature and pressure, let's just do this right away because this is right here. What is STP? Standard temperature and pressure. That is 273 Kelvin, which is the same as 0 degrees C, and 1 atmosphere pressure. Well, if you can just memorize this, or you can work it through PV equals nRT, the ideal gas law, if you look at 1 mole, the ideal gas constant of 0.0821 liter atmosphere over mole Kelvin, and remember you always want to stay in Kelvin for your ideal, for any of your gas laws. Put a 273 there, and you put a 1 atmosphere here. You'll always get for V, under these conditions, 22.4 liters. That's the molar volume of any gas at STP. Alright, so now I know that 1 mole of gas will occupy 22.4 liters. I've got 0.199 moles, so I will have less. So I'm going to take that 0.199 times 22.4 liters per mole to get my answer. My answer to this problem is 4.5 liters. Okay, so 1 mole of gas at STP, I know it's 22.4. That's on your resources sheet, but it's good to memorize it. Once you establish that you have 0.2 moles, we establish that by taking the count and dividing it by Avogadro's number to convert it to moles. We only have 0.2 moles, so we're going to have a fraction of this 22.4, which is 4.5 liters. Alright, so then this last question is the flip question. How many molecules of argon gas are in 30 liters? Alright, that 30 liters can be turned into moles by saying, well, there's 22.4 liters for 1 mole, and so I'm going to end up with slightly more than 1 mole. I have 1.34 moles here. And then how many molecules? Well, it's actually atoms of argon gas. That makes me want to use Avogadro's number. I have 6.022 times 10 to the 23 argons per mole, and that will lead to my answer, times 6.022 times 10 to the 23, and I'll get I need 3 sig figs, 8.07 times 10 to the 23 argon atoms. And that's your practice for Chapter 8. Let's move into Chapter 9, which was really the hardest chapter that we covered this semester. Alright, what I do here is I take the same reaction equation and I approach it from multiple ways. Let's first of all go through some vocabulary. With stoichiometry, it's really looking at quantifying chemical reactions. And so any two species in a chemical reaction can be related to each other through moles. So I want you to be on the lookout for the easiest case, which is moles to moles. If you have moles to moles, then you can go straight with the coefficient bridge. If you have grams to grams, you're going to have to convert to moles first, then use the coefficient bridge, and then convert from moles of B to grams of B through molar mass. Okay, so we're going to practice this each way. This is not really a workable question here, so kind of skip that one. Alright, what is theoretical yield? This is what stoichiometry, what stoich gives us. It's your perfect case scenario. What is limiting reactant is the reactant in least abundance. It's the one that will run out first. What's the percent yield? We take what we actually got and divide it by the perfect case. What stoichiometry said we should get, times 100%, and we'll see how close we were to perfect. Right, we have a sample problem below to do this. Alright, so I keep going over and over through the same reaction equation. 3H2 plus N2 leading to 2NH3. Okay, this is the formation of ammonia. And I picked this one because it has nice coefficients. Alright, what if you have 5 moles? I like to write right underneath it what we're given. If you have 5 moles of H2 and plenty of N2, which means don't worry about it, how many moles of NH3 will you produce? Alright, this is my favorite one because it's moles to moles, so it's really easy. All I do is apply the coefficient bridge. Okay, so to apply the coefficient bridge, I'm going to this one, so that goes on the top, and I'm from this one, so I'm multiplying by 2/3. So what's 5 times 2/3? Is 3.3 moles. So I'm just going to keep, even though I'm given 1 sig fig, it's 3.3 moles, just so it's approximately 3 moles of NH3 will be produced. Okay, moles to moles, easiest case. Alright, next up, same reaction equation, but I have 5 grams of H2 and plenty of N2, which is saying don't worry about it. How many grams of NH3 will we produce? Alright, so here's the grams to grams case. Please be alert to what you're provided and what you're being asked for. Okay? It's very crucial that you can categorize these successfully. Alright, I'm given 5 grams. I'm asked for how many grams of this I can get. You need to get to moles first, and so you'll take 5 grams times 1 mole of H2 is 2 grams, and so you have 2.5 moles of H2. So then I would write that right underneath here, keeping everything neat and tidy, okay? These periods hardly work. 2.5 moles of H2, and now we may use the coefficient bridge because we're in moles. So it's the same coefficient bridge of 2/3. Let me switch colors here. 2/3. And so I'll have 5/3, and that's 1.7 moles, but that's not my answer because I need to get to grams. 1.7 moles, it's really 1.67. Let me keep another sig fig. 1.67, and what's the molar mass of NH3? It's 14 and 3 more, it's 17, times 17 grams per mole. That will give me my answer in grams. Times 17, and I get 28.3 grams. I just have one sig fig, so we'd say about 30 grams. I'll keep the 28 there. Approximately 30 grams of NH3 will be produced if you start with 5 grams of H2. Alright, the last reaction on this screen right now has a limiting reactant, okay? Can you see this as a limiting reactant? You know it because you're given amounts of both reactants and you're not sure which one to work with, okay? So what we have to do is a side calculation first up to figure out which reactant is in less abundance. Now we've already done the work to figure out that we have 2.5 moles of H2 here. Let's figure out if we've got 10 grams. Let me put this underneath here. 10 grams of this, 5 grams of this. We already know that this is 2.5 moles. Better run out of space. And what's 10 divided by 28? Because the molar mass of N2 is 28. Well, that's only 0.357 moles. So what I do is I put a little star right here and recognize that that's my limiting reactant. So that says I'm going to use that one to do my calculations. So I'm already in moles, so I'm ready to do the coefficient bridge. What's the coefficient bridge here? 2 over 1. 2 moles of NH3 for every 1 mole of N2, because this is moles N2 times 2 moles NH3 over 1 mole N2 will convert me to moles of NH3. So I will have 0.714 moles NH3, but you were asked for grams, so we need to multiply times 17 grams per mole, and we will get our answer of 12, and we just have one sig fig, 12 grams of NH3. So you'd say approximately 10 grams of NH3 would be produced. That's 12 grams NH3. Let's move into theoretical percent yield. The theoretical yield is what stoichiometry gives you, and it was 12 grams. What if the actual is 8.5? Then the percent yield is what you actually got over theoretical times 100%. You would say the percent yield is 71%. It says there was some waste, there was some loss, and we didn't have perfect outcome of 100%. Alright, let's move into Chapter 10 with gases. You're going to have to solve a number of gas laws problems, and they're not all stated out on your resources sheet. If you look on your resources sheet, what you have is the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2, and then you will have the ideal gas law given. And I just want to, first of all, take a few moments to realize that you can generate everything you need from the combined gas law or the ideal gas law. Alright, sitting at the top of the ideal gas law are P1 V1 equals P2 V2. That's Boyle's. Okay? What it says is, what if temperature was constant? Then these in effect wouldn't be here, and that would be Boyle's law. Okay? Well, what if you had volume constant? You kept everything in a closed container and you wouldn't let volume vary, then the V1 and T1 would disappear, and then you would be left with Gay-Lussac's law relating temperature and pressure. And then finally, let's suppose pressure is held constant and the gas is allowed to expand or contract as needed. Pressure would go away and you would be left with Charles' law. So you only need to see the combined gas law to get all of the relationships that you need. What is an ideal gas? An ideal gas would be small molecules with no interaction, no bonds whatsoever, okay? No clumping, widely spread apart. And they move at high speeds. All of the gas laws apply to ideal gases such as these. The gases deviate from the gas laws when they start to set up interactions with each other or when they get big and bulky. What is the ideal gas constant? In PV equals nRT, the ideal gas constant is this R. It's a constant, okay? And most people remember this one for the rest of their life, 0.0821. The units are cumbersome. Liters times atmosphere over moles times Kelvin. Okay? Now it's possible that you're given, instead of atmospheres, you're given torr. If that's the case, where you're given torr, then atmospheres goes away and you'll have torrs, and this number changes by the factor of 760 because there's 760 torr in one atmosphere. So if you'd multiply 0.0821 times 760, you'll get the other value for R that's common, which is 62.34 liter torr over mole Kelvin. And then remember that torrs are the same thing as millimeters of mercury. They're synonymous. Okay, so we've done this. We've done this. That's general. We've done this. Remember to work in Kelvin when solving gas law problems. Absolutely, you got to remember that because you can't divide by zero. And then I have a couple problems here. A 5-liter sample of air is collected at 500 degrees C. Immediately switch this to Kelvin. Remember, you add 273 and 2 atmospheres. What's the volume at STP? What kind of a problem is this? Let's see. I know a volume. That's V1, we'll say. Here's T1, the original temperature, and the original pressure. What's the volume at STP's code for V2 equals, that's what we're finding, but T2 is 273, and P2 is 1 atmosphere. So we can see that this requires the combined gas law, P1 V1 over T1 equals P2 V2 over T2. Plug in all these numbers. Whoops, that's a 1. So P1 is 2 atmospheres. V1 is 5 liters. T1 is 773, really hot. P2 is 1 atmosphere. V2 is what I'm looking for, and then T2 is 273. You'll get V2 is 3.5 liters. We really only have one sig fig, so we'll say it's approximately 4 liters. We're limited by that too right there. How many molecules of hydrogen gas, remember hydrogen gas is diatomic, that's hydrogen gas, are in 1 mole? 1 mole of anything has 6.022 times 10 to the 23 molecules of H2. I guess I should. MOL is moles, so we have to write out the word molecules. Calculate the density of neon gas at STP. Well, density is mass over volume. Okay, at STP, I know the volume. It's 22.4 liters for a mole. Do I know the mass of a mole of neon? I sure do. It's sitting on the periodic table. It's 20.2 grams. Okay, this is for 1 mole. For 1 mole of neon, this is true. Well, density would be consistent throughout wherever you would find neon. At a certain temperature, you would have the same density. We find out that it's 0.90 grams per liter is the density of neon. If I would look at 2 moles, it would be double the volume. It ends up being characteristic of the material. So just remember this trick. You can find the density of a gas at STP because you know the volume at STP. Just go and get the molar mass off the periodic table. Those are your practice problems for Chapter 10. Let's move into liquids and solids. We have what's called the kinetic molecular theory. The kinetic molecular theory describes the 3 phases of matter. We've got the solid, the liquid, and the gas. The KMT says solids are soldiers lined up and closely associated. All they do is vibrate, and they set up strong intermolecular forces, IMFs, between each other. If these are ionic ions, they form an ionic solid, and then they actually form the ionic bond. If these are metal atoms, they set up tight metallic bonds with each other. But if these little circles represent a molecule, then they set up what are called IMFs, intermolecular forces. They're covalent compounds, and they set up IMFs, which are of 3 types: hydrogen bonds, dipole-dipole, or dispersion. Of these, hydrogen bonds are the strongest, dipole-dipole is the next strongest, and dispersion are weak, except if the molecule is very large, like proteins, the dispersion forces become significant because they operate along the length of the molecule. All right, back to the KMT. We're saying solids have strong interactions between the particles and vibrate only. Liquids are medium. They make and break their interactions, and they're moving around. They have some kinetic energy. So they're medium kinetic, medium bond energy. We'll call it bond energy. And then finally, gases are widely dispersed. They're bouncing off the walls of the container. They have lots of kinetic energy, and they have no bond energy. So let me just summarize this. 0 bond energy, high Ke. And then solids would be almost 0 Ke, and then very large bond energy. I'm using the term bond loosely. And then liquids would be in the middle. That's the characteristic of the 3 phases of matter. And what we're saying is, depending on the temperature, the temperature relates to the speed of the molecule or the particle. And so if they get slow, they actually are able to set up interactions between them. This causes clumping, and this causes them to become liquids or ultimately line up like soldiers as a solid. These interactions are how we get liquids and solids. If we didn't have interactions happening between the particles, you wouldn't have liquids and solids forming. In this chapter, we talked about unique properties of water. It's really important that you are clear that water has a bent structure because there are two unshared pairs of electrons off of the oxygen, okay, which makes it negative in this zone. It makes it possible for another water molecule to come up near that oxygen. The hydrogen would be attracted there because that's a negative zone and the hydrogen is in effect positive. And we set up what's called a hydrogen bond here. And the hydrogen network within water gives it unique properties, okay? We have high specific heat, okay? And that was in first semester when we talked about specific heat. But it's the amount of energy it takes to raise the 1 gram of material 1 degree Celsius. It's the heat, the ability of the material to respond to heat. We say water is very sluggish in warming up because it holds together as a network, and so to break these hydrogen bonds takes quite a lot of energy. Okay, so it has good resistance to heat, to temperature increases. We also say because of this network of hydrogen bonds, water has a very high boiling point and melting point compared to other members of its family. By that I mean compare water to this compound. See, sulfur sits right underneath oxygen on the periodic table, or this compound, selenium below sulfur, or tellurium under that. These compounds should all be similar, but what we see is that water has a very unique position in that its boiling point and melting point are very high, and that's because of the H bond capability. Remember, to have an H bond, the hydrogen must be on an oxygen, nitrogen, or a fluorine. Okay? So we're saying we've got an HO or an HN or an HF. If you have this situation, then H bonds are possible. That would eliminate these guys cannot H bond. Another thing we find is that water has a very high surface tension because of this network. And we would see that water has a low vapor pressure because it tends to hold together really well. All right, in a similar way, you'll be asked to rank compounds by the strength of their intermolecular forces, looking to see if they could possibly H bond or if they'd have dipole-dipole interactions. Let's look at these compounds and figure it out using these. PH3N2, Li2O, CO2, H2O. You have to categorize these compounds as to type. All right? So this PH3, I hope you see that as a covalent compound because I've got nonmetals. This is a covalent N2. It's just two nonmetals. This one is ionic. I've got a metal with a nonmetal. This one is covalent. This one is covalent. Alright, so my Li2O would be ionic, and this would be held together very strongly by ionic bond. Okay, so that's stronger than an IMF, an intermolecular force. That's a covalent thing. So the Li2O would have the highest melting point, highest boiling point. Let me put that above here. High melting point, high boiling point for an ionic compound like that. The rest of these that are all four covalent, how would you figure out which one would melt the highest or boil the highest? Well, we look at if there's any polarity in the molecule. All right, of these, let's first of all look for FON, okay? FON. That's our check to see if we could possibly have any H bonding. No. 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 Yes. Okay, on this list, water is the only one that could H bond. So this would be the next highest melting point. I'm just going to use melting point. Boiling point will be consistent. Alright, so far what we've said is that Li2O would be the greatest, and we've just distinguished that water would be next because it's the only one on this list of covalents that could form an H bond. Alright, we now move to dipole-dipole. There are certain criteria for dipole-dipole. Dipole-dipole says, in addition to the fact that there's got to be some polarity there, we have to lack symmetry. So the polarity of the bond has to also incorporate a lack of symmetry in the molecule so that it's lopsided with respect to charge. With lacking symmetry, remember, bent shapes and pyramid shapes are always lacking symmetry. So water, for instance, has a bent shape, and it is also dipole-dipole, but it has the greater hydrogen bond capability. So we put it down as being the next best because of the H bond. But if we look at what remains, we have CO2, N2, and pH3. Let's think about the polarity of these. All right, pH3, we'd have to draw this Lewis structure. P comes in with 5 valence electrons. Okay, and then your H's come around. So we see this as a 4-3 shape. This is a pyramid. Well, pyramids lack symmetry, so this guy is polar. Okay, so that's going to say this is going to be the next best choice on the high melting point, boiling point list. Okay, N2 is not going to lack symmetry because it's identical. It's 2 nitrogens. They're actually triple bonded with each other. That has no polarity. And then we've already used this guy. We've used this guy. We've used this one. CO2 is a little bit tricky because we see it as polar bonds. Okay, it ends up being like this. It's double bonded on each side, but it doesn't lack symmetry. So it ends up being nonpolar, and it will be equivalent to N2 in that it has dispersion forces only. Okay? Dispersion only. So let me recap this. When you're deciding between compounds, which would have the highest melting point, which would have the highest melting point, which would have the strongest intermolecular forces, in your mind you should go through a flow chart. First of all, you look to see if it's ionic bonded. That's the strongest. Metallic bonded, that's very strong too. If it's covalent, then we've got to sort through these 3 different types of intermolecular forces. Hydrogen bond being the greatest, dipole-dipole next, dispersion force last. You go through in your mind and categorize these compounds by what they're capable of. On this list, we picked out Li2O as the only thing that was ionic, and we knew that that would melt the highest. Next up on the list was the only compound that was capable of H bonding, which was water. Next on the list was there's only one compound on this list that's polar, as defined by it's got a pyramid shape, which is why it's polar. That's the pH3. And then the other 2 compounds are nonpolar, and they would have dispersion forces only, which is nitrogen gas and CO2 gas. And that becomes our rank list here. It's a little hard to see, of sorting them out this way.